Hello. In this section, section 1.2, we'll be talking about three things. So in the first section, in the last video, we talked about what a differential equation is. And so now we're going to talk about what it means to be a solution to an equation. We're not actually going to find solutions in this section, just talk about what it means to be a solution. We're also going to talk about a special type of a problem called an initial value problem. And then I'm going to prove a theorem about when solutions to a problem actually exist. So oftentimes it happens that you're not necessarily concerned with finding the solution of a differential equation, but more concerned with just knowing whether a solution even exists. So, not even dealing with the really hard part of finding that solution, but, could there be a solution in the first place? So as a reminder, we had kind of two different forms for what an ODE or ordinary differential equation looked like. So the first one is where all the terms up to the nth derivative of our function y are on the left-hand side, and then we have just 0 on the right-hand side. Or we might take the biggest derivative of y and pull it out and keep it on the left-hand side, either way. Now, I will note, too, that I have flipped up the notation from the last video to make it so that our independent variable is x instead of t. Sometimes you see it one way and sometimes you see it another, and I will do it all different ways throughout these videos, so yeah, keep you on your toes. So we have here our y is our dependent variable, and x is our independent variable. And then we also have n is the order of the equation, that's the highest order derivative. And then I want to really point out that y is the thing that we're looking for. It's our answer. So when we talk about the solution, it's y. That's what we're looking for. Now let's take a definition. We have a function phi of x. We have that Greek letter phi there in blue. We say that it is an explicit solution to an ODE in either of the forms that we showed on the last screen if it satisfies that equation for all x in some interval in the real line. So all the x between a and b. We don't want it to happen just at a single point, because that can happen and sort of not tell us anything. But we need it to happen in an interval so that there's sort of room to be changing over as x changes. If you're at a single point, you can't talk about a derivative. So let's take this equation as an example. This is a linear equation. And just as an aside, it may look a little bit funky, like you'd think it'd be nonlinear because this thing, but that is linear. This term here is nonlinear with respect to x, but because x is the independent variable, that doesn't matter. This is linear in y, which is the thing that matters, is that y and all of its derivatives aren't doing funky things like multiplying each other or getting raised to powers or things like that. So anyway, this is a linear ordinary differential equation, and we want to know something about the solutions to it. So let's take this example here. This phi, is this phi a solution to the equation? Well, what do we have to do? We have to plug it in. And if we do that, we would need to actually calculate our derivatives. And we can see that phi isn't even defined at x equals 0, but anywhere where x doesn't equal 0, then we're okay, and we can calculate our derivative. So I'll do that right now. So now we have our phis and our derivatives, and so we can plug it in, and that'll look something like phi double prime of x, or at least on our left-hand side, phi double prime of x minus 2 over x squared times phi of x. Okay, so anywhere we had a y in the green equation, we're going to put a phi instead. Well, what does that equal? Well, our phi double prime, we already calculated, 2 minus 2x to the negative 3, minus 2 over x squared times phi of x, which is this guy, minus x to the negative 1. If we simplify that, we'll leave the first bracket alone, 2 minus 2x to the negative 3, and we multiply through on the that 2 over x squared, and we get negative or minus bracket 2 minus 2x to the negative 3, and the two things in brackets are the same, so this equals 0. So we have a check mark. Yes, phi is a solution. I haven't really talked about the word explicit here, and this will become clear when I talk about implicit solutions in a second. But really what's making it explicit is that I have a definition, an explicit definition for what the function phi is. I have phi equals x squared minus x to the negative 1, and it is a solution to the ordinary differential equation. The one thing that I left out here, this is a solution on for x not equal to 0. So that we need to be on an interval, like I said earlier, so we can think about this solution exists for x in the interval from negative infinity to 0, but the open interval, as well as the interval, so that's a union, the interval from 0 to infinity. Okay, so let me do another example here. So let's say we have some other function, psi of x equals x cubed. Is it a solution? Well, let's try plugging it in. So first we'll take our derivatives. So those are easy enough to do, and then we will plug in. And so we get, we need to have psi double prime of x minus 2 over x squared times psi of x, and that equals 6x minus 2 over x squared x cubed. We simplify, and we get 6x minus 2x equals 4x. So the question is, we need this to equal 0. And this is only when x equals 0. Okay, so it does satisfy the equation at one point, and you see why. Maybe it makes sense now why we insist on having an interval, because if you only had it at one point, then this would be kind of like silly, because you want to say 4x equals 0. Well, no, obviously it doesn't. So the nice thing is that no psi of x is not a solution, and that's because x equals 0 is not an interval. So that helps us get rid of kind of trivial solutions. So now here's our next type of solution. Sometimes we can't find an explicit solution, but we will come up with a relation, g of xy equals 0, which might define an explicit solution. And so we call that type of relation an implicit solution. And that's a little bit weird, but let's show an example. So here's our problem. We're given this relation in green, which is not an explicitly defined function, but there is some set of ordered pairs, some values x and y, that satisfies the green equation. And that relationship defines a function where you can map the x's in the ordered pairs to the y's in the ordered pairs. So that's an implicitly defined function. And we want to show that that is an implicit solution to this nonlinear ODE in the blue. And we know this one is nonlinear, we can see, because there is this sort of like nonlinear behavior in the in y. So we have this e to the xy, which is a little wonky and makes this whole equation nonlinear. So now the key thing here is that y is still our dependent variable and x is our independent variable. And you may have learned and possibly forgotten from calculus that you can use implicit differentiation to find the derivative of a function y that is defined implicitly, like we have here. So we're looking for dy dx, and so we will take the derivative with respect to x of the whole left-hand side of the green equation up there, and we get d dx of x plus y plus e to the xy. And we'll do this term by term because we've got addition. So the derivative with respect to x of x is just 1. The derivative of this next term of y with respect to x is, the derivative of y with respect to x. And then the derivative of the e to the xy term, we have to use chain rule on. So the derivative of e to the xy is e to the xy times the derivative of the inside part, or of the xy part. So that's going to be y. So we'll take the derivative of x, which is 1, leave it, and then multiply that by y, plus leave x alone and take the derivative of y, which is dy dx. And then this will all equal 0 because that's the derivative of the right-hand side. So let me annotate this a bit. So the term over here is the derivative of the left-hand side of our green relationship. The 0 is the derivative of the right-hand side. And then you may want to pause and work out the details of my calculations here of how I use the chain rule and how I use the product rule. It's really just calculus. It's just kind of the notation that's a little weird. So anyway, I can simplify this down, and I get all of the terms that have, I'll pull out all the terms that have dy dx in it, and I get a 1 plus x e to the xy dy dx, plus the rest of my terms, I have a 1 plus a y e to the xy, and that all equals 0. And that is the ODE. So that's exactly what I was looking for and what I needed to prove. So what I have shown is that this implicitly defined function here, if you do implicit differentiation on it, then that shows that it satisfies the ordinary differential equation. And so that makes the green relationship here a solution to the ODE. Now, while we're talking about solutions, we'll talk about a special type of problem. So ODEs have to do with how quantities change over time, usually. And so how things are going to change over time will depend on how they start, right? So if you're talking about modeling population growth, how big is the population going to be over time? It depends on how big it was to start. So usually often you need to know what the initial values for the problem are, and not necessarily just for the function itself, but also its initial rates. So all the values for all of its derivatives. And so this is called an initial value problem. And so in this case, you will be given not only an ODE to solve, but also some values for what you had at a starting point. And so that starting point x naught is usually kind of the left end of the interval, but it might not be, because you could think about time going backwards. Anyway, it's some point in the interval, and you're given some constants, the y naught, y1, y2, blah, 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 for the initial values of all of the derivatives of your solution y. So let's do an example and find the solution to initial value problem. Here's our problem, our IVP, or initial value problem. We have our ODE in green, which with also our given initial conditions. And we're given a solution and we want to show that it is. So we're just going to plug it in so we can compute our derivatives. and then we can plug them into the equation. So our equation will look like we need it to be phi double prime of x plus phi of x, and that equals negative sine x plus cosine x. It's our first term, plus our phi, which is sine x minus cosine x. And we can see that the cosines cross out and the sine x's cancel out, and this equals 0. So we get a good check mark. So that's one thing that we have to check. The other thing is that we need to check the initial conditions. Okay, and so that's easy enough as well. So we just plug in phi of 0, because this is our sort of x naught up there. Phi of 0 equals sine of 0 minus cosine of 0 equals -1. So there's a check. And then we need to check phi prime of 0 will equal cosine of 0 plus sine of 0 equals 1, and that's what we wanted too. So we had 3 things to check. First, we had to check that phi satisfied the equation. Then we had to check that phi satisfied our first initial condition and then our second initial condition. And it will become clear as we start actually learning how to solve these equations and these problems, why the initial conditions sort of come up. And you can think about it now as when you did antiderivatives in calculus, you would have that plus c plus a constant, and you end up doing that same thing when you solve differential equations, because you can think about solving differential equations as doing antiderivatives. And so you end up with these constants, and if you know the initial conditions, then you can solve for those constants. So the one thing that we haven't done in this video is actually find the solution. We were given a solution or a potential solution, and then we proved that it in fact worked. But something that we want to know is something that will help us solve is if there is even any hope of finding a solution. And fortunately, there are some fairly general theorems that help us know that. So we're going to talk about one right now. So here's a theorem. Consider that you've got some initial value problem. And this is just a first order equation, first order differential equation with one initial condition, because you are only on the first order. So this theorem says that if the function f, which is not our solution y, it is the sort of combination of things in our ODE when we have it written in this form. So if f and its derivative are continuous functions in some area around the initial conditions x naught and y naught, then the initial value problem has a unique solution phi in some interval. Okay, so this gives us a thing to check to know if we might have a solution. And that big thing to check is that f and its derivative are continuous functions. So that's the key thing that you have to satisfy. So let me caveat this, or at least note a few things. So this theorem is only for first order equations, okay? Things, as you go up in higher order, things get crazier, and again, you sort of start off with what you can handle. So what's nice about this theorem is that the ODE doesn't have to be linear, but that condition on f and df dx being, or df dy being continuous says that the ODE can't get too crazy. Okay, it doesn't have to be super nice and linear, but it's got to have some element of niceness to it. Next, it only guarantees a solution for a little while after your initial condition. So it gives you that delta and some interval after your initial x naught, but that delta could be really, really, really small. So it tells you solutions exist for a little while, but not necessarily for, indefinitely. And the other thing is that it doesn't tell you how to find the solution, and it doesn't tell you when a solution doesn't exist. But at least, you have some way to start thinking like, okay, a solution exists. Maybe I should start worrying about how do I find it. So here's an example. Here's an ODE, and we want to know if this theorem is telling us anything. Does this satisfy the conditions of the theorem? So in order to make this look like the statement of the theorem, we want to get that dy, our highest order derivative, the dy dx, over on the left-hand side by itself. So in this notation, in the notation of the theorem, and so we just have to divide the 3 over. We get our f of xy, the right-hand side, is equal to 1/3 x squared minus 1/3 xy cubed. And of course, that's a continuous function on all values of x and y. And similarly, we can compute our derivative df dy. So this is the derivative of f. F is a function of two variables, x and y. So we want the derivative with respect to the y variable. And that's easy enough because we're taking the derivative with respect to y. The first term is just 0 because it doesn't change with respect to y. And then we get a negative xy squared. Remember, when you take partial derivatives with respect to y, you hold that x constant. And so this is great. These are both continuous on all of r squared. And thus the theorem implies that there exists a solution, phi of x. Okay, so now let's look at another example. So we've got the same question. Does the theorem imply the existence of a solution to this? And so in this case, we've already got our dy dx over on the left-hand side. So our f of xy is just the right-hand side, 3y to the 2/3. And this is continuous on all of r squared. So that's fine. And now our derivative, df dy of xy. So we don't even have an x in it, so that's no problem for us. So we get 2y to the negative 1/3. And this is continuous, except for, because we have a negative exponent here, we get like a 1 over the cube root of y. So this is continuous except where y equals 0. So the problem is that we need that y equals 0 is our initial condition. So that's exactly the point where we need this function to be continuous nearby. And so if we can't take that derivative at our initial condition, then we can't conclude anything. Now, if we had a different initial condition that was away from y equals 0, then we would be in good shape. But in this case, the theorem doesn't apply. That doesn't mean that there isn't a solution to this initial value problem. The theorem just doesn't tell us anything about it. And so that's sort of the deal with these existence theorems. So what we've done in this video is talk about what it means to be a solution and when solutions might exist. But what we haven't done yet is anything about how we would begin to find them. And so that's going to be the topic of our next section.